So this is what our 5th lecture in vapor power cycles, and we are covering basically the last topic. It's regenerative vapor power cycle. What does that mean, regenerative? Well, you're trying to preheat the feed water a lot, as high as you can get it, before it goes into the boiler or before you're paying for an external fuel source to heat it. So on the TS diagram, we could see that if you have some feed water that would be very low, just to throw some numbers out, like 60 degrees C, and eventually you're going to heat it up to the boiling point, maybe it's close to 300 degrees C, then get it to change phase, then heat it some more, maybe up to 440 degrees C, that this heating at low temperature is what's wasteful, what can be eliminated or reduced to improve efficiency. The heating at high temperature is good for performance, just from an entropy point of view, just from comparison with Carnot. Well, what did we learn? Bring as much heat into the cycle at high temperature and reject as much at low temperature. Rejecting it is typically in the condenser, and rejecting it out at 60 degrees C, just try and reduce it to 50 or something, but there's not a great improvement there. Just get the condenser pressure low, the condenser temperature low, and usually that's not too hard to do. But right here is a great opportunity. Ingenious engineers saw this somehow, somewhere, and they said, if we can preheat even half of that liquid, get it up to halfway, using internal source of heat somewhere in the cycle by re-diverting, diverting off some steam, that will help. And whoever did this the first, I'll have to say, is a genius. Now, it's probably done 150, 200 years ago or something, long time ago, but they were really insightful and figured that out. So one of the things you can do is, after it passes through a turbine, you can take and split some off and divert it, and then take back to the steam generator and reheat and go back into another turbine. So where do you go with that? Well, you're going to get the fluid out of the condenser, and you're going to mix it or have a heat exchanger. If you have a mixing heat exchanger, that's an open feed water heater. Open because the two fluid streams just mix and you have one out. Then you can get that preheated and get it away from that cold 60 degrees C before it gets into the boiler. All right, you can also have a closed feed water heater. There's two types of feed water heaters, isn't there? Now, the open, I think we covered last time, did I not? You're pretty comfortable with it? Good. Normally, you get the open before you get the closed. But you may, in a real power plant, have 2 or 3 or 4 turbine stages, and you might have 2 or 3 feed water heaters. You usually don't go bazonkers and get 18 turbine stages. Forget it. I don't even know if there's any 6 turbine stages out there for a real power plant. Nor do I know if there's 4 or 5. That just is too many feed water heaters. But just a few can really help improve performance, okay? So if you're going to have an open feed water heater, that's usually what you put in first, and then you put in maybe another open or put in a closed second. And you just have to solve some problems to see why. But this is an introductory class. Actually, we're trying to introduce a whole class in power plant design next semester, technical elective. If you're interested, I'm not teaching, but we're trying to recruit somebody to teach it, okay? But here are the 2 feed water heaters, just a simple mixing, and this one's the harder one to understand. Now, this one is a closed feed water heater. Think of the cold fluid coming in and coming out a little warmer, but it's still cold, right, compared to the hot fluid stream that maybe was diverted after the first turbine stage. And it's going to come through. And so the direction of heat transfer is from the hot fluid stream to the cold fluid stream. There is no mixing of the fluids. So one fluid is typically inside tubes. Do you understand that? They flow through tubes in the heat exchanger. And the other flows on the outside of the tubes. Well, that would be the shell side. So you may hear me say, oh, the fluid on the shell side and the fluid in the tube side of that heat exchanger. So the fluid that goes through the tubes here as shown is the cooler fluid, the colder fluid. But whatever comes in the tubes goes out the tubes. So the mass flow rate's the same. It's not the same as the hot fluid going on the shell side. That's a different mass flow rate, but that mass flow rate in here, let's call this state 1, is the same as out 2. And what's in at 3 is the same as out at 4. Okay, now, the way that this works is have a steam trap to hold back the liquid, because typically you bring in something that's either slightly superheated or it's high quality steam. You can get a lot of energy out of that steam if you get it to condense. And when it condenses on the tubes, the outside of the tubes, it's pumping heat into the fluid inside the tubes. Hopefully that makes sense. So you get it to condense, it's like giving up a lot of heat. This is a type of vernacular discussions people will have. And condensate will form in the bottom. Did I talk about what to do with that condensate and how a steam trap works last time? No? Well, a steam trap is a device that sounds funny by the name. Just like regenerative is a funny word for this type of enhancement to the vapor power cycle, steam trap is a new type of, when you're brand new to it, you say, well, who came up with that name? Understand the device before the name. What's it doing? It's basically monitoring the condensate level. And if the condensate level gets too high, it opens up and lets condensate flow through it. And can you tell by the little X right there really what it is then? A valve, a throttling valve, exactly. But it's not always open, and if all the condensate would go through and the steam says, hey, I'm next, let me go through, the valve closes. It traps back the steam. It won't let the steam go through, only condensate. No vapor through, only liquid. And there's some really ingenious devices. They've been around for a long time. They work. They're in a lot of plants and other things. And I encourage you, maybe I'll do it Monday. I'll go to YouTube and show you, because I've done in this class some YouTube clips from manufacturers, how they work. They're pretty neat, the engineering little devices. All right? But it's not that hard. It's like a float. You know, the level goes up, open it up. Float goes down, close the valve. But there's a pressure drop from here to here, isn't there? It's a pressure drop. So you're going to get a significant pressure drop across that valve, even when it's letting liquid through it. There's a pressure drop. Okay. So that's what a steam trap does. It basically forces only liquid to go through. Once you understand what they are, you understand how to basically go out into an actual power plant or other facility where they have steam and diagnose it. You can find that actually there's a lot of broken steam traps out there in practice. Not the good facilities where they have good engineers, but there's some other facilities where they just don't pay their engineers or the maintenance people. And anyway, there's a lot of broken steam traps out there who are that's letting vapor through when it shouldn't. So if you ever get out there and you have problems at a facility, a lot of times as an engineer, you're asked to go diagnose and find the problem and fix it, right? Hey, we're paying the engineer, they're the expert. If it's in a steam system, look at the steam traps carefully. Actually put an ultrasonic little meter down there and listen. And if it's steam's just blowing through it. All right, so there's a little hint for you. Let's go on. So we have a problem. And what we do is we have a word problem. And it could be, I'm not saying this is your exam on next week, Wednesday. It could be that I say, give me a sketch of the plant. Show me all the components. Give me the layout. And then once you've done the layout, number the states. And once you've told me how many states there are, you know, unique states around there for thermodynamic property calculations, then sketch it on a TS diagram. Fair game? Don't be surprised if it's on the exam. Starts with just the word problem. You have to read it and then decipher. So we have a regenerative. Once you see regenerative, you know there's either an open or a closed feed water heater. There's at least one. And then we have this 8 megapascal. Start noting your pressures. Okay, that's high. Oh, it's superheated. And then it comes out Oh, at 1 megapascal, that's the first turbine that must have multiple turbine stages. Then you go, some is diverted to an open feed water heater. You could even start sketching. Okay, I have an open feed water heater. I have my first turbine stage. I'm coming into it very hot, high pressure. It comes out, some is diverted down. What happens to the other? While the rest is reheated. Okay, I've got my steam generator right here. I'm going to go back for a little reheat, then I'm going to come out, and I'm anticipating going into the second turbine while the rest is reheated back to a high temperature, 440 at 1 megapascal, and then enters the second turbine. Saturated liquid leaves the condenser. There's no information about another feed water heater. There's no information about a third turbine stage. It's after that when you put it into the condenser, and then we know what comes out, saturated liquid. We put it into a pump. What are we going to do with the pump? We're going to blow it into the open feed water heater. That makes sense to me. Open feed water heater has 2 ins, 1 out. I'm going to have to put another pump to pump it up, to feed it back to the steam generator. And there you go. There's my cycle. And then we're going ahead and put states on there. There's state 1, there's state 2, there's state 3, there's state 4. I make it look easy, don't I? But there's a lot of decision making about, hey, where's the state? 6, 7, and then 8. And then right away, there's some critical observations like, can you tell me and maybe put a note right here about the condition of state 5? Coming out of the condenser, it's saturated liquid. Saturated liquid. How about before this second pump right here, what is the condition of state 7? The best is saturated liquid. There's a lot, a knowledge that goes behind those statements, right? There's a lot that we already learned about this. Why we want to feed it saturated liquid, good for performance. Why not feed it some 2-phase liquid vapor mixture? No, don't do that. Pumps don't run that way. All right. We can go ahead and maybe mark the high pressures. What states have the high pressure of 8 megapascal? 8 and 1. How about 7? That's the intermediate pressure. All right. How many have the lowest pressure, the condenser pressure of 20 kilopascal? Do I say 20 kilopascal? Yeah. 4 and 5. How about 6? No, that's intermediate. The hard ones, I think, are the intermediate pressures. Is 6 the same as 7? The same as 2 and the same as 3? That's right. So you get your pressures, you get your idea of all the states. The other thing you want to do is go ahead and sketch it on a TS diagram. It's pretty symmetric. The constant pressure line of 8 megapascal, and then it's fairly steep. I usually draw it too shallow. And then a constant pressure line of, what's my intermediate pressure? 1 megapascal. So 1 megapascal, 8 megapascal. You want to get good at drawing this, sketching this, right? And then the other one is 20 kilopascal, 20 kPa. Now you got to start to put some numbers for temperatures. Having your steam table or solving a number of problems, can you tell me what is the temperature of the condensate coming out of the condenser? What is Tsat for 20 kilopascal? See that? This is my temperature entropy diagram. What is this temperature that matches the 20 kilopascal? 60-ish. That's right. I don't need it more accurate than that. 60-ish. So there you go. Then you say, what is maybe the saturation temperature for 1 megapascal? 180-ish? 180-ish? Is that it? You solve a few problems, Professor, I'd memorize this. No, you just become familiar because you solved a lot of problems. All right. Who has a steam table? Can you please look it up? 179 point something. 180-ish, okay? 180-ish. Now, what is the saturation temperature for 8 megapascal, our boiler? Or how about from memory? Anybody? Just a smidgen under 300. 295. Close it up to 300 for me. I usually say 300. So we have ideas of our temperatures. Now you have 3 lines of constant pressure, ideas of temperatures. You can put every one of these states on the diagram. Where is state 1? Well, it's up here at 440 and 8 megapascal. True? Where is state 2? Isentropic expansion through the first turbine stage from that state 1 to a lower pressure. Where is state 2? Straight down, right? So we drop it straight down. A lot of times it'll come in where it's high quality steam in the dome. Sometimes it'll be over here. You have to be careful. Sometimes it could be superheated steam, slightly superheated steam coming out of that first turbine. Every problem's different. But this is a good way to draw it at state 2. What happens? We then put it back to the reheat, so it goes and then passes up. It could stop somewhere at a lower temperature, or it could go all the way up, back up to 440 again. If it goes all the way back up to 440, there's state 3. And then we expand it. As I've shown it for 4, it goes superheated. You see that? As I've shown it for 4. I passed out an actual TS diagram. You can actually put these states on that actual TS diagram. True? Did you get a copy of the TS diagram I passed out? And then you could chase it. But in the interest of time, I know I want to solve another problem, so let me rush on. Where is state 5? Right over here. Where is state 6? This is where a lot of students will get it wrong, but you won't, will you? Where is state 6? That's after this first pump. Less than 1 degree higher and same S. And so it's like right there is state 6.
It's not on the intermediate pressure line?
It is, but that would be a gross, most books do it that way, but it's gross exaggeration of the delta T. All right, you're right. Okay, how about state 7? This one's hard. Saturated liquid at what pressure? You got it. Once you got that, it's easy, huh? Saturated liquid. Every point on this dome on the left coming down from the critical point is all saturated liquid. It's got to be somewhere on that edge of that dome, and it's at that pressure of 1 megapascal. It's right there. Got it? Then we have state 8, go through the pump. Same idea. We'll show it as a gross exaggeration, and up there it goes. That's state 8. And the idea is, it used to be that you had all of this heating going from 60 degrees up to nearly 300, 295 degrees. But with the advent of the Feedwater heater, all of this is gotten rid of, and now you just have this amount of heating before it starts to boil. And now you have this amount as it boils. That hasn't changed. And this amount of heating to get it up to be superheated vapor. So that hasn't changed either, from the saturated vapor to superheated vapor. But you've reduced how much is just to get it up to the boiling point in the steam generator. Good for performance. Very good, right? Once you've got the schematic and the TS diagram, you're ready to put it all in a property table. Get the property table going. If you get the property table going, I like to have a column over here that tells me little notes, like tells me how do I fix state 1, how do I fix state 2, what allows me to determine it. But the most important part of this table, I want the column of H's. Oh, I've got to tag along with the entropies because, oh, it's isentropic expansion, constant S. But I really want the H's. I need those enthalpies. You know what? I can get all of those enthalpies. I can just march around the system and calculate them. It's a lot of work. But you have to be able to do that, okay? And now we come back here, and there's one property, Y. What does that symbol Y indicate? The mass fraction that's diverted to feed the open feed water heater. How do we calculate Y? Well, it'll be a function of the H's, but how do I get the equation so I can calculate a numeric value for Y for my problem? Do a control volume analysis. This is music to my ears. You're making the instructor so happy. Can you tell I'm happy? It's like, yes, yes, that's it, right? So I do a little control volume around here, and I do both a mass balance and an energy balance. Let me do this because I want to walk through a mass balance. The one way after you work with the masses is you could talk about the mass going in and out of each device, or you can also talk the mass going in or out of each device normalized by the mass that goes into the first turbine. If you do that, then you're just talking dimensionless numbers, like 1 is 100%. So 1 is 100% of what goes into the turbine. What comes out? 100%. But then Y is the fraction that gets diverted. So what continues? 1 minus Y. That's like a mass balance. It's telling me 1 minus Y continues. 1 minus Y goes into the second turbine. 1 minus Y comes out of the second turbine and goes into the condenser. 1 minus Y goes into the pump. 1 minus Y comes out of the pump and goes into the open feed water heater where it mixes with Y coming from the top. And what comes out of the open feed water heater, I'm doing a mass balance, back to 100%. And then you're back to 100% out of the pump and then through the steam generator on the first pass. It's 100%. And we're going to need those in a second. All right. That's like a mass balance, not just for the open feed water heater, but for everything, the whole cycle. Because if you did the mass balance just for the open feed water heater using this, it would be like Y coming in from the top plus 1 minus Y coming in from the side equals to 1 going out. And isn't that equation true? It's like 1 is equal to 1. Yup, things work. Now, when you do the energy balance, you're thinking that I know I did this last time, right? So we're going to just do it in terms of this Y, a little more abstract. But we have H2 coming in with Y. We have H6 coming in with 1 minus Y. And it goes out only H7 times 100%. That's one equation with one unknown. What's my unknown? Y. I want to calculate Y. So I know that I'm not that great at algebra, but I think you could do the algebra here. Would it be like H7 minus H6 divided by H2 minus H6? Is that my equation for Y? Professor, I would really appreciate if you gave me that equation if you give me this problem on the test. That chance, no way. No way. Well, then I'm going to have to write it in my notes. No notes, no notes. Well, then how am I going to know this equation, Professor? Isn't engineering plug and chug? No, you got a wrong perception of engineering. You're going to have to rederive it. All right? And I may ask you to say, I may say, show your work. All right. All right, so once I have all the H's and I calculate the Y's, for this problem, what is the percent diverted down to feed it? Around 20%. What continues in the loop? Oh, around 90%. 1 minus Y is 90%, or not 90, what did I say? It's around 80%, okay? Now I'm ready to calculate for each component the heat and the work transfers in and out of those components. True? So why do I have 4 columns? 2 of them are just Q and W, and then 2 of them are Q asterisk and W asterisk. Why do I have this little asterisk down here? Because I'm going to do it on the mass that goes through that component, and then I'm going to modify it to it's the mass that goes through the first turbine stage. Why would I do that? So everything's on the common mass flow rate. Everything's back to what goes through the first turbine stage, because what goes through the condenser is not what goes through the first turbine stage. Can you tell if 1 kilogram per second goes through the turbine, 1 kilogram per second goes through the first turbine stage? What goes through the condenser? How many kilograms per second? 0.79, around 80%. So that's why I encourage you to have 4 columns. All right, so if I just said right here, I know these are the 3 parts of the boiler, but they sum up to the total for the boiler. So just focus on the total for the boiler. Right here's the total for the boiler, right? So what is the Q going into the working fluid in the boiler? Sometimes I call it steam generator, but is it the H coming out, state 1, minus the H going in? What was that, 8? I can't remember my numbering. Is it 8 coming? Okay, good. Is that how I got this number right here? Right. Now, notice that I already populated this, but Q star, this is how many kilojoules per kilogram of what goes through the steam generator. But if it went through the steam generator, it's the same flow that goes into the first turbine, so I don't modify that. These two are the same, aren't they? True? All right. Now, let's take a look at the reheat, though. If I say, what's the heat transfer into the working fluid that goes through the reheater? Well, that would be Q reheat would be H, 3 minus H2? I'm trying to remember my numbering. Right? But that's per kilogram that goes through the reheater. But of the fluid that goes through the turbine, only 80% goes to the reheat. 1 minus Y goes to the reheat. So how did you get this number, Professor? Multiplied by 1 minus Y. Oh, you can do it in one step, but logically I think it's helpful to do it in 2 steps. True? All right. How about this for the condenser? What's that fraction? 1 minus Y. Yes, sir.
Is Q dot N considered the sum of those 2 numbers, what you get?
Yeah. When we come down here to do the thermal efficiency, don't forget that you're adding heat here and you're adding heat there in the thermal efficiency. Is that what your question is getting at? Yes. So if you want this thermal efficiency, if theta is equal to the W net of the cycle out compared to Q in the first pass of the steam generator plus Q of the reheat, and you're going to do everything per the same unit mass flow rate. All right, now let me get over here. So the work for the first turbine is the same, but the work for the second turbine is not the same. What's the difference? 1 minus Y. 1 minus Y. And then for the pumps, I know you really don't see much of a difference, but it's the same thing, 1 minus Y. But it's the same for the second pump because everything goes through the second pump. It's joined back up. But for the first pump, it's only 1 minus Y. And then why did I color code this one and that one? Well, look at if you compare them. That's the net heat into the fluid for the cycle. This is the net work out of the fluid for the cycle, all on the same per unit mass flow rate, which is through the steam first turbine, and they're the same. See that?
And that's always going to be the case for regenerative reheat?
All cycles, not even just regenerative, right? And that is an error check. If you don't get those to be the same, find your error, right? And then notice, are these 2 numbers the same? No, because they don't have the same mass flow rate. Each one of those Qs is either there's 2 mass flow rates really to think about. All right. Then you can calculate the back work ratio and the thermal efficiency. Yes.
Why is your Q net star, why is it larger than just Q net?
Because of the reheat.
You added the reheat to it?
Yeah.
Okay, so you reheat.
Yeah. Well, this is a huge negative number, but that's on the wrong per unit mass flow rate. So this number is not meaningful. It's just not meaningful. All right? Okay. Here is a kind of looking into why this helps performance. because you reduce the amount of heat just to bring the liquid up to the boiling point. We started with this system at 181 instead of down by 60 degrees. You know, it's already from 60 to 181 was accomplished without any external fuel source. So we've reduced to 22% that heat needed in the steam generator to preheat the liquid. Well, we change it to a closed feed water heater. The only thing you have to worry about, again, is you have the tube fluid is not mixed with the shell side fluid. The shell side fluid usually does the condensing, hence the liquid collects, and then you only let the liquid go out. Often it's trapped, put a steam trap to a lower pressure. Once you have it there, you need to do something with it. You can dump it in a condenser, you can dump it at somewhere else, another feed water heater, an open feed water heater. Another enhancement that you could do is you say, if this is liquid, saturated liquid, why don't I put it through a pump? Good idea. Sometimes they do. And then you would have it high pressure, you would put it and mix it here, and away you go. So there's not just one layout of a power plant, there's multiple. You have a choice as a designer. So you could put a pump and handle that condensate that way, or you could put a steam trap. The only thing is you can't let that pump draw down the liquid so much that you're drawing in vapor. You've got to only let saturated liquid go through the pump, just like the steam trap. Okay, now what we want to do is we want to calculate Y needed for this device, for this system. True? It's a different equation than the equation we had before. And let me just say that you have to pick the condition here coming out of that closed feed water heater in order to have an equation to calculate Y. Okay? Either I give you the equation for Y now and then talk about state 7, or talk about state 7 and then get the equation of Y. What do you want? All right, let me do this. What is the pressure at state 7? Can you tell? It's the highest pressure. Maybe it's the 8 megapascal. All right. What is the temperature at state 7 that makes most sense? Oh, if we were about ready to shove it into a pump, we'd want it to be saturated liquid. Nope, can't use that logic anymore. Well, let me do this. Let's do this. If we had this pressure right here to be, what was it, 2 megapascal in the previous problem? And it came out with the quality at state 2 was, 99%, right? Can you tell me roughly the temperature at state 2?
It will be the temperature sat at.
T sat at the 2 megapascal. Can somebody remind me from the steam tables the saturation temperature at 2 megapascal? 212? So it's around 212 degrees C. All right. This comes out at state 8, true? Okay, tell me the pressure at state 8 that comes out. State 8, that's the shell side, remember? 2 to 8, that's all on the shell side. What is the pressure at 8? 2 megapascal. True? It's 2 megapascal. It's coming out condensate. What is the temperature of the fluid coming out at state 8? 212 degrees C. You have gained a lot of information in this class plus the prerequisite class, because there's a lot of knowledge that goes behind those statements. Now, think about it. The hot fluid coming in is 212. It's going out at 212. It didn't change temperature. It couldn't have transferred any heat out of it. This is all bogus. No, it comes out of it because it's condensing, right? All that steam condenses at the same pressure, same temperature, and there's a lot of heat transfer out of it. Well, how about the cold fluid? Let's say this comes in around 60 degrees C. This is around 61 degrees C. What do you think? Is it going to come out at 61 degrees C? That'd be a pretty poor heat exchanger. All right, wow, I'm going to bring it up to boil, maybe I'm going to eventually get it up to 295 degrees C to start boiling. How about if we bring it out at 290 degrees C? Is there any reason that you can't bring it out at 290 degrees C?
Yeah, your heat source is 212.
Your heat source is 212. That's a brilliant statement. You ain't going to get it out at 290. Professor, I can run the calculation and I can get a numeric answer. Yeah, but that's your computer code. In the real world, the hot of the whole thing in the heat exchanger is 212. So what do you think? You're going to be able to get the cold fluid out greater temperature than the hot fluid ever was? No. And so often, the hot fluid out is limited to be no more than the cold fluid out is limited no more than the hot fluid temperature. So maybe you take 5 off of it or 10 degrees off of it. Maybe this comes out at 200 degrees C at a state 7. Does that make sense? Does that make sense? Maybe you can get it to easily because there's always a 12 degree delta T to drive the heat transfer. Professor, let's say I just put in my calculations, it comes out 250. Well, do a second law analysis, and probably you've done something like destroyed entropy. Not generated. Probably broke the second law of thermodynamics. That's my guess. But from a heat exchanger, it's always from hot to cold. All right. So now that we understand that usually the temperature and pressure of state 7 are fixed, they're specified in the problem statement when you have a closed feed water heater. And that may seem a little awkward, like why did they pick 200? Well, it's about 12 degrees less than 212, that's why. All right, now that I can calculate Y, so what do I do here is I do first a mass balance around Y, and I do it for the whole system. So if this is Y, let me clean this up a little bit. If this is Y right there, isn't it 1 minus Y that goes to the reheat, 1 minus Y through the second turbine, 1 minus Y through the condenser? True? But this is a steam trap. What comes out of the shell side is Y. What goes through the steam trap, Y. So when they 2 ends into the condenser, what comes out at 5 going into the pump? 1 again. Brilliant. That's a very good observation. Not 1 minus Y, it's 1. And then it's 1, and then it's 1. Now we got our mass flow rates. Let's do the energy balance around this closed feed water heater. So we're going to have H2 times Y, and we're going to bring in H5 times 1. No, that's 6, isn't it? 6. H6 times 1. That's 2 N's equal to H8 times Y plus H7. That's 2 outs. That's my energy balance. I know you need to start and then manipulate a few steps to get there, okay? Show your work. Right? But here we'll put Y now is just going to be a simple equation. It's going to be what? H7 minus H6 and then H2 minus H8. There you go. Make sense? All right. Press forward. Would you have the same equation for Y for this system? Just looking at it.
Is that closed or open?
This is an open feed water heater. Oh, that's a closed. I'm sorry, you're right. It's a closed. Here's the cold fluid, and here's the hot fluid. Would it have the same, because it's 2 and 8, 6 and 7, the same numbers?
6 is 1 minus Y.
It's not the same. Because this is going to be 1 minus Y on the mass flow rate, 1 minus Y out. They mix out over here. Different equation for the Y.
Is it the same assumption to say that saturated liquid always enters the trap, steam trap?
It's saturated liquid is what comes into the steam trap. Yes, that is the way the steam trap works. It holds back and makes sure only sat liquid gets into it, right? And it's a pressure drop. Did I show a pump? Well, the trap's not here. This is the pump. Same thing to the pump. Back here, this is always saturated liquid. State 8.
And it's the nice and velvet.
That's another great observation. Professor, what's the relationship between H9 and H8? He just said it. There's a few steps to go through that to make that analysis. That's all prereq thermo 1, isn't it? And you do the analysis and you find, oh, it's isenthalpic. Whoa, wow, I got new words now. Can't wait till my friends try and ask me what I learned in thermodynamics. I'm going to use that word. No, come on. I'm just having fun, right? Isenthalpic. It's constant enthalpy. So the H on the outlet of that steam trap is the same as the H on the inlet. I'm rushing a little bit, and it doesn't matter how much I rush, I don't make it. I wanted to solve and set up a problem that was more complex. I apologize. But you notice what I did here in bold. I stressed that when you have a closed feedwater heater, the outlet to the closed feedwater heater, both the temperature, and usually the pressure is restated, but it's obvious what the pressure is. But the temperature is a critical temperature. All right? All right. You have a question?
Is there any way you could work it and upload it to YouTube? Just watch it.
I have Monday.
When you say the 210 is the critical temperature, is that like...
No, it's specified in the problem statement. And if that temperature, if T11 isn't below T2, you probably got a problem. It needs to be below T2. And believe me, I made enough homework problems and exam problems, and I've made that mistake. But it's been a long time since I made that mistake and then give it to a student. Because what do? They struggle with it, and they say, Professor, I got a negative Y. Yeah, okay, well, or I got entropy, destruction going on in this. Oh boy, I messed up on that problem. All right, other questions while we got a minute or two?
Were you able to get through this in the morning section?
I don't recall, actually. Here, I'll do this. There was a question of why it can't be 250. I just answered that. Give an equation for y1. You need y1 right here, and you need an equation for y2. You should be able to get those equations. And sketch it on the TS diagram, and here's the results. I'll put this up. So right here, what do I have right here for y1? That's the equation for y1 and the numeric value for this problem. And this is the equation for y2 and the numeric value, as well as all the h's, as well as all the q stars, w stars, as well as the back work and the efficiency of the cycle. I know there's a lot of work. So I'm going to probably solve this problem Monday in detail, but I'll probably post this up just like this on YouTube for you. Thank you. Have a great, safe weekend.